All right, our last talk of the day is Seth Naman, a fisheries biologist with NOAA Fisheries, and he's going to talk about a method to implement a natural flow regimes for regulated rivers. Seth earned a Bachelor's of Science from Oregon State University and a Master's of Science in Fisheries Biology from Humboldt State University. After positions with Idaho Fish and Game, the National Park Service, and the Yurok Tribe, he began working for the National Marine Fisheries Service in 2008. Seth participated in several of the TRRP's work groups, the Trinity River Hatchery Technical Team, and he's an alternate on the TMC. He is a longtime resident of Humboldt County and enjoys fishing, hunting, kayaking, and rafting. And welcome, Seth.
That was a old bio from somewhere. I don't know where you dredged that up. Well, thanks everyone. I know I'm the last talk of the day here, so thanks for sticking with me. I'm really excited to be here. Really excited to talk about something that I'm passionate about. Nick is passionate about. Something we're very excited to share with folks. I'd like to start with some acknowledgments, just briefly. You know, the record of decision at the time in 2000, it was groundbreaking. It was based on the best available science with over a decade or more of study. It secured water volumes for the river. It really initiated the Trinity River Restoration Program, and in some ways, the record of decision is why we're all here today. So, did a lot of good things. I'd also like to acknowledge the work that the Hoopa Valley Tribe put into that record of decision. And I know for the Hoopa Valley Tribe, the record of decision was, it was like a treaty, or it was to them a treaty. And I understand the importance of that to them. I would also like to acknowledge Ken Linke, Kyle DiGiulio, and Justin Alvarez, who helped kind of package up some of the stuff I'm going to talk about as a NEPA alternative for the upcoming consultation that's going on between Bureau of Reclamation and National Marine Fisheries Service. And Nick couldn't be here today. He had to go back to teach a class. So I'm going to give the second half of his talk today also. So I got an outline for today. A clicker here too. What's it? The red dot? Okay. Brief outline, just the background information. I'm going to go over, kind of do a little bit of a deep dive into the alteration of the Trinity River hydrology over time, the ecological effects of that flow alteration, some of them, and the real-time flow management method that we're excited to share with you today, and some results. You know, I'd like to start this talk just by saying there have been, as other people have mentioned, people that have been here since time immemorial that have used the resources of the river. Trinity Dam, a lot of this background I'm going to blast through. Trinity Dam was built and began partial regulation in 1961. That's a picture of it right there, and the hatchery with Lewiston Dam also. I know you guys have already seen a bunch of this stuff today. And Derek showed a graph of this, but this is basically the average inflow into Trinity Reservoir is 1.2 million acre feet. The Trinity River gets about half of it going this way. The other half goes to Whiskeytown Reservoir. These are the rod flow hydrographs. Right here, there's 5 water year types. I know a lot of you have already seen a bunch of this in the last few days. There's basically, this is meant to mimic like a snowmelt hydrograph. And as you can see, the extremely wet water years are shifted to the right, because the thinking is, as you have more, when there's more snow, it melts slower, and so you have with more snow, you have a longer duration of snowmelt. I'm going to talk about some gauges today, focus on a few gauges in this area. One of them is Salmon River at Sums Bar, the other Trinity River above Coffee Creek, and then Trinity River at Lewiston, the one of most interest. But I'm going to focus mainly on Salmon River at Sums Bar, but also Trinity River above Coffee Creek. And importantly, they all share common ridge lines. And basically, when our storms typically come from the west, like winter storms come from the west or the north, sometimes from the south, more infrequently, rarely from the east. So generally, when they come from the west like that, they're affecting all these gauges in this area in the same way. And this is just a graph from 1958 showing the response of these three gauges to storms throughout that year. Importantly, Trinity River above Coffee Creek and Salmon River at Sums Bar are not dammed. Here's the period of record for those. We're very lucky to have Salmon River at Sums Bar and Trinity River at Lewiston, both starting in water year 1912. And all of the streams are rain and snow runoff dominated with a very low base flow index. Streams that have a high base flow index would be like Shasta River, McLeod, Pitt River, where you have a big spring or groundwater influence. I'm going to use time periods similar to what Eli talked about, 4 different time periods, although mine are, I think, slightly different. Maybe the pre-dam, I think Eli showed you, went to 1961. I use 1960. But anyway, those are the 4 periods I'm going to break some of these analyses into. And I'd just like to state that, there's a ton of papers out there on what happens when you dam a river. And, there's a quote there that basically simplistic and static environmental flow rules are going to lead to further degradation of river systems. Obviously, the seminal paper by Dr. Leroy Pop, The Natural Flow Regime, was, I think a big milestone in river management that a lot of people have read or know about. So I'm going to talk about this, what I call the 50% date. And it's just a date at which 50% of the flow volume has gone down the river. If you made a flow duration curve, it'd be like the 50th percentile date on a flow duration curve. And we're just going to look at it this way. So the Salmon River, this is a Salmon River at Sums Bar. And in 2016, that 50% date was March 5th. You get about half the flow before March 5th, about half the flow after. So Trinity River at Lewiston in 2016, that 50% date was May 20th, about 8 weeks later than the Salmon River at Sums Bar. And these are all of those 50% dates going back to 1912. So some things I want to point out. The biggest thing is that this is when the record of decision was initiated. And after that date, that 50% date was almost always in May. And it was basically always later than the Trinity River at Lewiston. It was never in the pre-dam record. It was never as late as the dates in the rod period. Here's the averages, the average date of those. So you can see the rod May 11th, whereas in the pre-dam era for Trinity River at Lewiston was April 7th. So we really shifted this date a lot later by shifting all of that proportion of flow to the right. Also, these real low dates here are all extremely wet water years. And interestingly, even when you have a lot of snowpack and you shift your hydrograph, like in the rod, shift it to the right, that's actually only for the snowmelt portion, and it's a little bit counterintuitive, but in an extremely wet water year here, the distribution of flows across the individual water year, that 50% day is actually earlier in extremely wet water years. So then when you overlay these rod hydrographs, with the, wetter being shifted further to the right, it actually shifts it further away from how it would be naturally. So here's what the negative correlation of two hydrographs looks like. So in 2016, our record of decision releases in 2016 were negatively correlated with Salmon River at Sums Bar. Part of that's probably our summer flows, but as you can see, it's a complete mismatch, a complete decoupling of the hydrology. And so here's all of those correlations going back to 1912. And what you see, this is the pre-dam era here. And the correlation between Trinity River at Lewiston, Salmon River at Sums Bar is 0.86, pretty good. It's a couple years here are kind of low, but overall stable and high. And then when the dam was built, those just fell out. And then we got a bunch of years in which there's like these negative correlations. So, Salmon River, all the hydrology, basically all the rivers in the area are coming down, and then jack flows up. And so in the rod era, the rod really didn't fix that. And that average correlation between these two gauges is 0.17 from the pre-dam era of 0.86. This is a base flow index. Todd told me he'd buy me a 6-pack of beer if I put this in here, and so I did. But basically the idea here, so all these streams I said have a low base flow index, all of them, Trinity River, Lewiston, and Trinity above Coffee Creek, Salmon River at Sums Bar, very low base flow index, 0.69. And as you can see, when the dam is built, that's this blue line, that went way up. And now even in the rod era, 0.36. As a hydrologist, we've essentially recategorized the Trinity River to be a groundwater dominated basin or a spring fed stream. And this is what you're seeing here is a representation of what Todd was talking about, how we have basically really unnaturally high flows in the summer. Coefficient of variation, not a huge story here. I'm going to kind of gloss over this, but this is when the dam was built right here. So the coefficient of variation got a lot more variable, and it's more variable in the rod era, although the average is about the same, 1.1 or something like that. But you can see historically the coefficient of variation is within a narrow band of around 1 or 1.2, and then the dam really screwed that up, and it's still more variable, which is a counterintuitive result that I don't want to get too deep into the weeds on. So some of the ecological effects of dam release asynchrony, there's just like this huge list, right? I mean, we could develop, you saw Don's, what Don was talking about, what Todd said, Eli said earlier, others, there's just this, a huge list that could go on forever. I'm going to talk about, that box didn't really work right. It's supposed to be up there, reduced sediment transport. I'm going to talk about reduced sediment transport and, unnatural tributary for delta formation for that matter. We'll see if this one works. Here's another big list. I'm going to talk about suppressed growth of juvenile salmonids. I'm going to touch on that because Eli really covered it really well. And I'm also going to talk a little bit about the lack of flows and triggers for juveniles and fries. So this is a picture of Deadwood Creek. Todd took these pictures back in 2019. And Deadwood Creek is the first tributary that comes into the Trinity River below Lewiston Dam. In 2018, there was a car fire, and the car fire came up from the Reading side, I believe, and then it burned down into the headwaters of Deadwood Creek and made these big fire scars in Deadwood Creek. And then we had a big storm in March of 2019, and that was the first year that there was following the storm. And in that year there was a paper by USGS staff over that studied drainages in Whiskeytown, and sediment loads in some of the creeks over there were up to 64 times greater than pre-fire sediment loads. So what happened was during that fire, Deadwood Creek blew out like this. If you study rivers, you spend a lot of time on rivers. Another thing that might strike you about this picture that was really weird for me when I went up and looked at it in 2023, the delta of this creek goes upstream. So you know you got a problem when your tributary delta is moving upstream like that. And it's because the Trinity River at Lewiston was 300 CFS during that whole time period, very low. So it can't transport any of this sediment at all. And what Todd found was that in that time, there was 733 reds between there and Rush Creek, where some of that sediment could get mobilized. And we think probably a very high proportion of those, certainly the ones that are near the creek, were complete mortality for Chinook salmon reds. And the same thing happened in 2023. And and I believe this year also, essentially it's been happening each year since then. And I took these pictures, that's James right there. And this is in 2023, that type of sediment on top of the reds is going to assure almost 0% survival, because you have both sediment oxygen demand. So the matter is decaying and it's using oxygen when it decays on the reds. And then you also have less water velocity over the eggs. And so the salmon eggs just die. Here's the georeference red locations. This is from the U.S. Fish and Wildlife Service staff and others who do red surveys up here. Each one of these dots is a red location. That's the Deadwood Creek confluence. So certainly all of these reds in here, probably 100% mortality for the ones that are the eggs in there that are closest to the creek. Moving on to poor temperatures for salmoniid growth. You saw this graph earlier. I had another one in here I took out just for sake of time. But basically, what Eli showed you is that these are the modeled flows for 2000 through 2018 without the dam. So you can just see how much more time and these are each years, how much more time each one of these years would have spent inside that dark band, which is the optimal temperature for juvenile growth. And we've been found on other rivers, they can grow even just as good or even better up here if they have enough food. As Don mentioned, they're poikilotherms. Or as Todd mentioned, they can use these different areas to go and digest their food and grow even faster. So there was only in the rod era, there was only 9% of days for all of these years where our temperatures were in the optimal juvenile growth range. And then you saw, if you were here yesterday, you saw Bill Penix's talk, the fish are smaller now. So after the rod era, we made more fish, but they're smaller. And so if their survival out to sea is nonlinear, then we might just be creating a lot of smolts that don't survive that well. I want to touch on the portfolio effect just a little bit here. I had some more slides, but I had to take stuff out in terms of time. This is from example from Sturrock et al., who did a paper on the Stanislaus River. And basically what I wanted to show here was that here's the pre-dam flows, and here's the post-dam flows here. And then what they did was they looked at the difference in flows. So basically during that period when they're storing water in the reservoir and not releasing any water, the difference in flows between those two periods is down in these months. It's up during where you have this par period, but then down again during the smolt time period as they bring the flows down. Shaded areas are the peak fry migration period. And basically what they found was that the flow regime on the Stanislaus is really only serving the par life stage, and it's and there's basically no flow or very low flows for the fry and also the smolts. And you can read some of those quotes over there, but basically the flow regime is decoupled from the unimpaired hydrograph. And if some of these fry would have survived, they'd have a lot better recruitment. And this just shows that basically as flow variability increased, the recruits produced per spawner also increased, and less variable flows were associated with reduced fish production. So these are all of the pre-dam Trinity River at Lewiston pre-dam flows, and 1912 to 1960. And this is the portfolio, if you will, the hydrologic portfolio that salmon evolved to. Highly variable. And when you give them that big portfolio, they have a big suite of life histories to adapt to that. Except we basically took all of that and eliminated all of the winter flows and then pushed everything over here to the right. So we compressed the habitat going down this way. We compressed it going that way. And if you remember the temperature graph that Eli showed, where we historically had this big range of temperatures like this, and then now with the dam flows, it's much more muted out. We squashed the temperature portfolio of the river as well. So when you do that, you essentially reduce the phenotypic and genetic diversity of all of the animals in the river. This is a graph from a paper, Naman et al. 2008, no relation. This is Robert J. Naman, which a lot of you probably know, really well-known researcher. It's spelled different too. But what's interesting about this, I found this paper, I was reading through it. They have an example from South Africa and an example from the Trinity River, California. And here's I'll just read this real. Comparative ability of natural environmental flows to create and maintain U.S. Pacific salmon habitat and Q spawning, shown as a hypothetical hydrograph that largely mimics temporal discharge patterns of the Trinity River, California, and the life history requirements of Chinook salmon. So this was a theoretical hydrograph that they suggested could be released to support all the fish. What I want to point out is that this theoretical hydrograph is completely synchronized with the actual hydrograph here. When they drew the theoretical hydrograph, they didn't draw like a big peak here when flows were low, or have their theoretical hydrograph shifted way out here to the right. Their theoretical hydrograph of what would be best for the Trinity River back in 2008 was a synchronized flow regime. And so Nick and I really wanted to try and operationalize this and think about ways, how can we do this? How can we get this done? So that's the question, is can we implement a real-time flow regime mimicking nature? And the whole idea is to basically piggyback on discharge signals from proximal gauges carefully. And if you think about it, Lewiston discharge is just it's really just a multiple of any one of these gauges. So if you were trying to meet this red line with this black line, you'd multiply it by, say, 0.5. If you were trying to meet this red line using this black line, you'd multiply it by 2, right? It's kind of, in essence, it's that simple, but it's a little more complicated. The model that we developed, it uses, we have all these constraints, right, that we can't get around. And one of them is our flow minimums. Okay, so the least underspending, and it minimizes basically habitat availability during rearing and outmigration. So how does it work exactly? Well, it's almost as simple as I mentioned before, where you have a parameter that gets optimized times the B120 water volumes for that month times the Salmon River at Sums Bar flow for that day, and that gives you the Lewiston flow for that day. Except we can do this for, say, like 3 days in advance also. It works fine with the California Nevada River Forecast Center forecasting tools. And then we can also disaggregate these into hourly once you have the daily flows. So would we get some complaints? Probably, but a big one I wanted to talk about was what Eli mentioned, how, we're going to have more rainfall, less snowpack, and that's going to increase flooding. Well, if every drop of water that gets released in the winter reduces the probability of spill, we're basically helping with flood control and spill risk, and it actually has benefits to reservoir levels later in the spring. So let's see, the model did pretty well, pretty much most of the time, and these are actually calculated for Trinity River above Coffee Creek because we used that as well in another run. You could use any creek. You could even just use precipitation itself, and the multipliers will get optimized. But 94% of the years we were within 10% of those water year volumes. And sometimes in dry years, the model wouldn't spend all of the water, but we can work on that. Some years we have this crash to minimums. But what I would say about, I did also want to point out, like, here's a 2015. 2015, our model put the river up to almost 8,000 CFS in a dry year. And one of the problems with using like quartiles, medians, averages, all these things is that this is the type of variability you miss. So in a rod hydrograph, you'd only go to 4,500. So just imagine the geomorphic work that we could do by mimicking what's going on in nature. But anyway, these crash to minimums that's going on in the model here, like in this year, 2012, here's a normal water year. Oh, sorry, the blue line is Salmon River at Sums Bar. The black line is the RTM result. And so, right in here, April is when the water year is designated. Like in this year, we already know what the water year is going to be. So we can stand back in this, like these last tails, we can sit back, the flow work group can shape these however they want. So just some results. For 2016, the RTM results shifted the 50% date 8 weeks earlier to March 10th. I think the Salmon River at Sums Bar was March 5th. In this case, the correlation went from negative 0.13 to 79%. And then these are all of those correlations again, same graph you saw before, except over here, the RTM results for correlation between the RTM results and Salmon River at Sums Bar. Not totally, I guess not a totally novel idea considering we use that gauge to develop the flows, but still it's a big improvement in mimicking the local hydrology over the past era, going from 0.17 here to 0.68 for correlation all those years. Never a negative correlation either, and in some of these years up to 80% correlation with local hydrology. For the 50% annual volume date, that was shifted down from May 11th, almost a month on average, to April 12th. So this here is the record of decision after the last flows, and we shifted that down overall met those wet years a lot better. And then suspended sediment transport, wanted to talk about this a little bit. And so basically the sediment transport is, though these are log scales here, so it's quite a bit greater for suspended sediment, again, for fine sediment and coarse sediment as well. I know I'm about done here. For the 2019 example, for when the Carr Fire came over the hill in 2018, and then the river blew out here, or the Deadwood Creek blew out, using the real-time management tool, be right in here around March 25th or something in here. Flows were 1,315 CFS, and they came up again to like 3,500 a week later. That would have been more than enough to get this sediment out of there, and probably millions of salmonid eggs would have survived better. That's it. Those are all the 2004 to 2023. That's what all the RTM years look like. Nice and messy, like we like it.